Hello, everybody. Happy Monday. How are you all doing? I can see that Necra and Kevin are here. They've joined us today. I was just asking before I started the camera button, did many of you get a chance to have a quick look at Nathan's blog post before we go through? No problem if not, because we're going to go through it together and absolutely step through it as well afterwards. So one thing I will say, I noticed my little signal bars in Restream keep flashing between red and green. So if my audio drops or something funny happens, drop a message in the chat. I'm keeping an eye out, so hopefully it'll all be fine. So just a quick survey before we get cracking. How many of you have come across HDBSCAN before? HDBSCAN clustering? Just curious. This was I saw Nathan's blog post and I hadn't come across it before. So today I had a quick look at it and I have to tell you, I am super excited. So I can see why Nathan found it really exciting. It's a super exciting clustering technique. Oh, don't worry, Kevin. We're gonna do a quick high level skim of what it is, and then we're gonna do step by step as Nathan instructs us in a bit. Okay, so right, let's have a quick go through what we're going to be doing today. So what we're going to do, I'm going to give you a super quick introduction to HDBSCAN. So this is going to be based on a very handy video I saw on from PyData 2018. So I had a quick Google, and for me, I quite like if I can watch a video or something. I like the sort of pictorial things. So absolutely, I like when I can go into deep depth and read stuff. So Nathan's got a lot of great stuff describing what this is and some great resources. I quickly had a look for videos as well today, and now I'm going to go away and then dedicate excellent quality time to really thoroughly read through this and understand everything that's going on. But there's a handy video there, and the quick introduction I'm going to go through uses some slides I've screen captured. So go and have a look at the video. It's really, really good. So Necro, DB-scan. Oh, yes. So you're half of the way there. You're already going to know a lot of this. So you're going to be our online expert, aren't you? So Necro's going to be our HDBC scan expert in this session. So it's all going to be fun. And then we're going to go through Nathan's blog post. So let me just quickly pop some links in if you do not have access. So first link is Nathan's article. That's going in the chat now. And let's give you the YouTube link, which I'm referring to. So it's about, without the questions, it's about 25 minutes. So let's have a look at that. Oh, sorry, we're not going to watch the video, but it's about 25 minutes and about 10 minutes of Q&A. So it's well worth watching. I found it quite useful, especially if you know some of the clustering things like k-nearest neighbors, and they mention a mixture of Gaussians as well as another example. So it's quite useful for that. The link to the video too. Yes, Necro. So yes, absolutely. So you've got that, and I believe you've got it in. Oh, it's one of the other ski learn. You're going to have to forgive me. I'm going. That's one of my missions for this year. Is I'm going to go off and do a lot of stuff in Python and understand all the common libraries, because I love all of this kind of stuff. And this is all coming from when, when I did this stuff many years ago, it was in C++. So things are a lot easier and nicer these days, and there's a lot more choice and range, and really exciting things have come up. So I really want to go off and do that. Yeah, it's a great blog post, isn't it, Kevin? Excellent. Joe's joined us as well. You're in for a treat as well. So the H is hierarchical. So we're going to go through that. I've forgotten what the acronym is already, but it's fine. We can Google the acronym, but we can talk around it in detail. So quick question. Kevin, I'll get back to you regarding your other question. So watch this space and yeah. But not now. Okay, so let's get started. So that video which I posted, I think it's very good. It's a really nice primer, and it describes different categories of clustering algorithms. So I very much recommend it. And what's really nice, what's described here, and I will dig out the name of the presenter. It was very good fun. But effectively, what he talks about is you've got this matrix almost of different clustering techniques. So you've got this idea of this centroid parametric clustering. So what means by that? So it's something along the lines of finding out how your data points are meeting towards, sort of like looking at averages across all the data points against other data points and looking where they sit. And parametric, you kind of have to give it some detail. So if you recall, and there's some nice diagrams we're going to have a look at in a bit. If you recall, for example, with k-means, we did a video on that about, was it 2-3 months ago? Again, it was another one of Nathan Smith's posts, which is great fun. So k-means is probably one of the most commonly known clustering algorithms. And the k-means is great. It's a very cool, neat idea. So it's this idea that you say, I think I've got this many clusters in my data. So you're going to give it a parameter. So let's say I think I've got 4 or 6. Actually, because we've got pictures coming in. I think I've got 6 clusters in my data. And then k-means goes away and says, well, okay, I'm now going to figure out what the distance is between every single point in my data set. And then, sorry, not quite. Sorry, I lied there. I lied a bit. So what it'll do is it'll arbitrarily, depending on your start point, it will go off and pick 6 means or 6 starting points for an average. So it'll pick 6 points, randomly, or there's some other clever things about how it selects those points. And then for each point, it goes away and figures out the average, the distance between every single other point. And then basically it goes, well, okay, well, these points are, all these points are closest to this arbitrary cluster point. So we're going to say that one. Well, these ones are closest to this one, so we pull it that. And then it recalculates the mean. So then you get a new 6 means. And then it keeps going that process over and over and over and over again until eventually it goes, you're settled. In a perfect world. There are some peculiarities around that. I'm not going to go into that detail, but roughly that's what's happening. But the main point there is it's centroid driven. So it's this idea that you're trying to find the distances of everything and how they're close. So it's a global calculation. You have to do this calculation, this global calculation across your entire data, all of your data points. And you have to have an idea of how many clusters you've got in there. Gaussian, I think they're saying this is Gaussian, I can't remember, it's a mixture of Gaussians, Gaussian multiple mixture, I can't remember exactly the acronym there, but similar idea. So the idea is you say, well, I think I've got this many Gaussian distributions in my data, and it's the idea of trying to figure out which points fit to which one of those distributions. So that's what's going on there. And it's this idea of flat, and the idea of flat is, I'm probably going to butcher the description here, or make more sense when we see the pictures. But there's this idea that the clusters are localized. There's no kind of clusters within clusters. It's either it's a cluster or it's another cluster, or it's this idea of you don't have this idea of clusters within clusters. So you've got those two. Then you've got this other set, this flat, which Joe and Netcro have both come across before. So they've got some experience in this, which is DBSCAN. And we've got mean shift as well. So mean shift, I believe, is equivalent to a running average. So I'm not going to go into that until I double check that is what I think it is. But you've got density and non-parametric. So the non-parametric bit is we don't need to declare how many clusters we think are in our data set, because this is going to, based on, we still have to put some parameters in, but based on a threshold or something that we put in, it's going to come back and tell us how many clusters they think there is. And it's this density idea. And the density idea, and what's really cool and quite exciting about this, is that it allows for this idea that maybe not everything, maybe not every single data point that we have is part of a cluster. Maybe we just have some outlier points. Maybe we have some noise. We have some junk data points that have appeared for whatever reason. And again, based on what we've specified as our density, that's going, that's going to effectively say whether some points belong together in some kind of a cluster or they don't. Great, so good so far. Again, please do correct me if I'm not saying the right thing. It's all good. I know we've got some experienced folk here. Then we've got the hierarchical one. So I don't know a huge amount about the ward complete linkage. That's something I'm going to go away and do a bit of research on. But the hierarchical component, and we've got a diagram for this, is this idea of saying, well, you can have clusters within clusters. So I'm going to pick a random one off the top of my head because I was thinking about where I'm going to be thinking about applying these methods in a later video. Ooh, fun, exciting. I'm looking forward to it. So if you recall, some of you, we've done stuff on wine and we've done stuff on recipes. So the BBC Good Food Guide data. And if you think about, let's pick the wine one, for example, and you think, well, we can have clusters within clusters there, can't we? Because let's think about the geographies. So you could have a cluster that says United States, France, etc. So those could be clusters, but you can have clusters within those clusters. So for United States, we're going to have things like California, and I'm really failing miserably at some other wine-making regions in the US. So if anyone wants to shout, oh, I know there is one in Vermont. I think Vermont makes some wine as well. So, so we could be splitting up. So those could be clusters, standalone clusters in their own right, but they fit under this hierarchy of United States. And then you think about California, that can break down again. We've got Napa Valley. So, and we'll have other categories in there and potentially have more. So you can think about have these sort of these clusters, but they have hierarchies in them. So you've got the ward complete linkage, where that is again this sort of centroid parametric. So you kind of have to say, well, I think I've got this many clusters. You have to say something along the lines of this centroid, this idea of the gravity of the points and the distance between them and how they come together. And then you've got the hierarchical density non-parametric clustering, which is HDBSCAN. So it is DBSCAN, but with hierarchies. Surprise! I bet you were all surprised by that. You all saw that one coming. So, and the idea of this is we have the good stuff around, not having to specify ahead of time how many clusters we think there are, and this idea of moving away from this sort of looking at all of the data points in their entirety from a global scale to figure out how far apart they are and what distribution they sit in. And it's more of a localized where the points sit. And this is where it's really exciting because this is like really graphy, really, really graphy. It's, to me, it feels like, as Nathan says, it smells graphy. It looks graphy. It's very exciting. So let's have a look at some pictures because I think pictures tell pictures are worth 1,000 words. So let's have a look at some of these. So let's have a look at k-means. So here's some data. And what's interesting here, so we can see we've got 1, 2, 3, 4, 5, 6. We've got 6 clusters here that have been identified. We've run k-means on this. We said ahead of time, we think we've got 6 clusters here. So we've put in 6. We've run this. It's gone away. And bearing in mind that k-means can be running over a number of dimensions. So this could be obviously more than just the 2 dimensions. So there could be a number of dimensions that we're trying to work out the distance of each point. And so we can say here, okay, so we've said that there's 6 clusters. K-means has gone away. Let's, for argument's sake, say we arbitrarily picked 6 random points and then did the iteration of finding out all the points that were closest to that one and then recalculating the average. And we just kept going and we settled at somewhere. And this was our output. So the thing to notice straight away that's interesting here is notice that every single point has been allocated to a cluster. So in k-means, there's no sense of noise. Every single point has been allocated to some kind of cluster. And let's take this blue one here, for example. So you can see here, these ones, I mean, I don't think anyone's going to argue. They're all tightly knit together and you go, yeah, that makes sense. Completely makes sense. The same cluster. But what's really interesting, if we start having a look at some of these points, you're like, don't know, maybe they're part of the cluster or not. Who knows? But the point being is every single point is associated in the cluster, and that could be good enough. So the point I'm putting here is that everything has thresholds, nothing's black and white, but it's all good. So we've got this. So that's k-means. So k-means, we have to tell it how many clusters we think there are, and we have to say, and everything gets allocated to a cluster. There is no concept of noise here. Let's have a look at DBSCAN. So what's really interesting here with DBSCAN, so we've got here, looks like we've got 1, 2, 3, 4 clusters. So we didn't have to tell DBSCAN how many points we've got. And the interesting thing with how DBSCAN works that is different to k-means is, whereas k-means we allocate 6, we say we've got 6 clusters, great. It then goes away and we pick either randomly or slightly less randomly 6 starting points, then we keep doing the entire the data points, and we go, right, which ones are closest to which clusters, right, recalculate, mean that stuff. What happens here with DBSCAN is it looks to its neighbours. So let's say we've said something like, we think that there should be something like, if to be classed as density or a dense number of neighbours or something to be classed as a cluster, you need to have X points or something like that, and that's set by, I think it was an epsilon threshold here. So you're gonna have to apologise. I'm talking from the high level stuff and the details a bit coming through. And oh dear, what happened there? Okay, I hope I'm still everything's still working. And the interesting thing is, what DBSCAN does is it goes, well, okay, we go for each point, and we try and find who are our nearest neighbours. That sounds graphic there, doesn't it? We're looking for our nearest neighbour points. So we're not trying to say, how does this point over? And this is assuming it was, again, this is multidimensional. This could be a fallacy. Maybe they sit next to each other. But anyway, we've got this point here and this point over here. We're not going to go away and calculate the distance between these 2 points. Effectively, what happens is it's a bit like a crystal growing. They go for a point and it'll go, well, okay, so what's my nearest neighbour? And then another point go, what's my nearest neighbour? And then another one go, what's my nearest neighbour? And if you've got like 3 or 4 of them sort of like clicking together, then you can start to see, well, okay, that's where you're starting to grow your cluster. It's a bit like crystals growing, how they all sort of like attach and grow together. And so this has happened with a threshold that's been provided. And it's gone, I think we've got 4 clusters. And what Kevin has said, it looks like the 5th cluster is noise. Yeah, quite possibly. So again, I need to look into the specifics of how the algorithm works. But the point being here is that these ones have not met the density criteria, the density threshold. So they've not been included in the cluster. So you can start seeing that's really powerful where, given a certain threshold, maybe you don't want to collect everything. So that's really cool. And okay, so that's DBSCAN. So let's have a look at the other one. So this is not quite, we've got a pretty picture as well, but I thought this diagram was really handy. So now we're looking at these hierarchical ideas, and the hierarchy is, I think it was really well described in the video. I really loved the example that was provided, which was, imagine, if you will, you're in an area where you've got tidal river or tidal sea or something. And if you think about the sea, so you think about the seas at high tide, so really, really high tide. And as the tide slowly drops, you'll see a bit of land. And as the tide keeps dropping a bit more, maybe other bits of land start popping up. And now you have you start off with 1 island, maybe now we've got 3 islands. And as the tide keeps dropping, we've got 4 or 5 islands. And as the tide keeps dropping, eventually, if the tide dropped completely, we'd be back to like 1 cluster. So everything's part of the same cluster. So this is where this whole idea of figuring out where do you need to slice your threshold with regards to, at what point do you call, at what point do you call the difference between the groups and the noise? So let's have a quick look at this. So here is the algomerative clustering. And you can see what's going on here. So it's that same idea. Notice how we had with k-means. Everything, it's it was parameterized. So in that sense, we had to say where we were going to slice, at what point do we slice the things. And you can see that everything belongs to a community. So here we've got, again, 1, 2, 3, 4, 5, 6 communities. But we had to say how many, we had to say where we were slicing. At what point did we cut the water level, and said, yep, we're good. And let's look at HDBSCAN. So HDBSCAN here, as you can see, we've got 6 clusters. And the idea here is the idea that we can have hierarchies within clusters. So again, some kind of threshold would have been set, but the idea being that I think we had where it said there was 2. Go back to this one. So here it was saying this was one cluster, and this was also another cluster. If you look in this one here, you can see it's separated out these into their own separate clusters. So you've got 6. So this is really fun. I know, Kevin, I'm so excited. Like today was like, what article we're going to cover today? And I always love Nathan's articles. He does some really amazing stuff. I've learned a lot. And I saw this one on HDBSCAN. I thought, okay, let's have a quick look. So I looked around. I was like, I can't wait to try this out on so many things. So yeah, it's amazing. So there you go. That is our very, very rushed overview of that. Watch the video. He explains it much better. And let's go straight into Nathan's article. Okay, so let's scroll up to the top. So yeah, so Nathan has mentioned loads of resources. Please do go check them out. And then we have to figure out where we're going to apply this. So we're going to use the Game of Thrones data set, which Nathan uses here in the article. But we've got to do some collective thinking about where we're going to do this, because I think we're going to have some great fun with this. And so it talks about it and the differences. So the idea is you don't have to decide how many clusters in advance you've got. And we talked a little bit as well about how we can avoid some of those outlier points as well. So that's really exciting. And the other thing that I'm super excited about, so I had a look at this article and I'm just like, so many ideas. So we're going to have a busy year ahead of us, I can tell you. We're going to have to be having some fun on Twitch. So I had a look at that as well. So it was like great fun. So we're not doing anything in Python. So it's in, so you got the various things here. For those of you who are using Python, you have got those links. We're going to be doing it in Neo4j. You'll be surprised to hear. Okay, so you have these 5 elements. So we talked about this a bit. So transform the space. Okay, that makes sense. We've got some stuff. What we need to do is put it into some kind of dimensions, because all of these things are assuming that we've got a number of dimensions associated with our data. So we've got some data in a graph. We need to do some kind of transformation to that. We're then going to build the minimum spanning tree. So you know how we talked about this is quite graphy, and how both the DBSCAN and HDBSCAN look at, oh, you're a neighbour to me, you're my closest neighbour, and so on. And that's what we're going to be using minimum spanning tree. So what minimum spanning tree does is it tries to figure out what is the fewest and the shortest number of connections you need to connect every single data point that you've got in your data set. So that's what's going to happen. We're going to build out the cluster hierarchy. So what HDBSCAN does is it tries to figure out what are your sensible clusters. So that's what's going to happen. Condense the cluster tree. So the interesting thing here as well, which again is explained in the video very nicely, is this idea of, well, what part of the tree of your hierarchy do you pick as part of your cluster? So I haven't got a handy diagram, but let's picture an example here. So let's imagine we've got a tree, and the tree has got 3 branches that come off it. And then we have another branch with 2 branches that come off it. So the idea is if we pick the 2 branches that come off that branch, we can't go back down the parent. That's it. But if we go from the parent, pick the parent, then we can't go up those 2. So the idea is you kind of, wherever you go, you kind of stop at that point. So I'm going to do some condensing, and then we're going to extract the clusters. Right. Excellent. So let's do this. We're going to do this in Sandbox. Sandbox is really great. if you've not had a go with Sandbox, please do. It's brilliant. You don't have to download anything. You don't have to install anything. Everything's handy there. And Nathan uses the Game of Thrones dataset, which is in the Graph Data Science one. So I have already done that. So if anybody wants to join me, now is a good time to get your Sandbox set up. So go to sandbox.neo4j.com and you want the Graph Data Science one. So we'll give it a couple. So if you're joining in, put in the link now in the chat. Got a couple of moments to quickly get yourselves set up. So we're going to be doing that. So let's do it with Sandbox. And we're going to do various bits and pieces. So I'll just give you a couple of moments. If you've got any questions, fire them in whilst any of you who are joining in can quickly get those sandboxes spun up. Right. Okay. So what we're going to be doing, we are going to be using node similarity algorithm for our custom distance metric. That makes sense. So what we're going to be doing is we are going to be finding some node similarity. What happens there is, as the name suggests, we give it a set of nodes. So Nathan here talks about a bipartite graph. So what a bipartite graph means is we've got two different categories. Oh, we've got a question here. Too bad I can't have any more. You can, you just can't have two sandboxes of the same use case, Necra. So what I would suggest is if you've not made any changes, I assume you must already have the Graph Data Science sandbox up and running. If you do, then just, as long as you've not changed the data, then just use that. If you have, then I believe the blank sandbox, oh no, we need the data set. So if you finish with that sandbox, you'll probably, I'd suggest you, and you've changed the data, then get rid of it and then start again. So you can get rid of a sandbox by going to the little down arrow here, and then you have an option here which says terminate, and then you can spin up another one. Otherwise, watch log, throw feedback in. But you, as long as you've not got the same, so you can't have two sandboxes of the same use case, but you can have, yes, Necros, you could have a blank one. But the only problem is that we're using the data set on the game, the data set on the Graph Data Science library one. So as long as if you've deleted that data, or you need to save that sandbox, and you might need to just watch along, and I will, that's a thing on me to then figure out how I can get you the data set for Game of Thrones next time. I will take a note of that and we'll figure out what we can do if you've already got the sandbox running and using it for something else. Okay, so with node similarity, you've got the bipartite graph. So what bipartite graph means is that we've got two different categories of node. And so you will use things like node similarity for things like just trying to recommend different things. So let's say, for example, I could create a bipartite graph of customer and product, and I'm interested in the relationship of customer buying a product. So my bipartite graph, because I've got two nodes, whereas a monopartite graph would be, I've only got one node category, so it could be customer. So if I wanted to know how customers are connected to other customers, maybe that would be a monopartite graph would load. This node similarities is bipartite, so this is where we're looking for similarities. So things like we would try to figure out, are customers similar to each other based on the products that they are buying? So, for example, if we had stuff like customer A buys shorts and t-shirts and sunglasses and a baseball cap, and customer B buys sunglasses and shorts and a t-shirt and a baseball cap, node similarity would go, well, looks at the intersection of those ones and go, oh, well, 100% same links. Well, you know, you know similar. And you might use that kind of information for figuring out things like product groups. So if you're building a recommendation engine and then somebody else goes off and buys a t-shirt, baseball cap, and a pair of shorts, you would probably say, would you be interested in some sunglasses there? Probably going on holiday. Oh, holiday, 2022. Okay, so that's the idea. So that's your bipartite graph. And oh, that's a quick section. It seems I can have my blank custom one and run. Yes, you can. So you can have, as long as you have two different sandboxes, you can run them. You just can't have two of the same at the same time. Okay, so that's that. So what we're going to do, so what we're saying here, we're saying if two characters are similar. And oh yeah, by the way, you could do this. So you can do similarity on two people. So if you think about it, I think the example that's going to be used here is you could figure out groups. So I think that's what's happening here. So we're looking at social interactions and groups. So we're going to do this. Let's follow those instructions. So let me launch browser first of all. Almost there. And this is it. So let's talk about what's going on here. So this is where we're going to be creating a graph projection. So we've got the graph data science library. You tell the algorithm what do you need to do the work. So we've got our data in the database. So this will be our Game of Thrones. And at some point, I will read the Wikipedia article on Game of Thrones. So I know who all the characters are. Yes, I'm probably like the only person on the planet who has not watched or read the series. So I do apologize. So what we're going to do here is we're going to project the data, and this allows us to check the data how we need it for the purposes of running our algorithms. So here what we're doing, we are creating our graph projection called GOT graph, and we're saying what we want. So here we're specifying the node label. So here we want person. We want our person nodes. I think we may have books in there. I'll remind myself. We want the person nodes. And then what we're saying here is we also want the relationship. So we want the relationship of type interacts. So the data set that's in there is all about the different characters in the book and whether they interact with another character. And what we're saying here is we want the interacts relationship type. We're not worried about the direction. Direction doesn't matter. And the aggregation is sum. So what we're saying is somebody, let's say character A has interacted, has 12 interaction relationships. Somebody else is like, wrong one. So the sum there is we're aggregating the property weight on the relationship. And here we're going to yield the graph name, the node count, and relationship count. So what we are doing here is this will just tell us the graph name. So it's going to tell us GOT graph, how many nodes, and the number of relationships. So there we go. That's great. If browser up, there we go. So I'm just going to ignore all this stuff, but let's just quickly have a look at let's have a look at our data. So if I just do core db.schema. Oh, look, there we go. So yes, I know we've got a lot of nodes, but bearing in mind that these are all, so apart from book, all of these are book and house maybe. All of these are king, person, knight. Okay, king, person, knight. So those are our people nodes. And we have some other nodes as well, which are, I think, descriptive. So let's not worry about that. We only care about the people. So the person, they will have like knight and person. Knight node will have a person label. So that's all good. Right. Okay. Let's get us a graph projection. Okay, there we go. We have 2,166 nodes, and we have got about 2.5 that in relationships. That's okay. So average relationships of 2.5. Obviously, not all characters some characters are going to maybe only have one. Some may have many. We'll have a look at the statistics next time. Love to play with that. Okay, so what we're going to do here, we are going to. Okay, we're going to be writing relationship between the nodes. So we're going to similarity. So this is going to be the function that we're going to be writing. We're going to be making changes to the graph. And what we're going to be doing here is we're going to be creating a similar to relationship between the two characters. And we're going to put a score between 0 to 1, depending on how similar they are to each other. Because we want a dense graph, okay, to write up to 50 similar relationships to each node. Okay, right, let's do this and have a look at what happens. Give that a run. Okay. Oof, we have written 33,000 relationships. So, we've got a quick question that has come in. You know what? I keep forgetting I've got this funky button. Hang on, let's do this. Can we use this to find influencers of the network? So we wouldn't necessarily use this approach. So this is going to help us find clusters. So this would be good for things like if we wanted to try and predict. So maybe not necessarily with this, maybe. I need to read the books to understand what's going on. But for example, if we were trying to figure out likely friend groups, this might be useful because this is going to have a look at how different groups are kind of gluing together. So you have your little community. So I don't know, if you were trying to do, you were throwing a massive wedding in 2025 with loads and loads of guests, and you wanted to figure out a good way of splitting people up so that you don't put people who are not likely to talk to each other on the same table, then this might be a helpful approach. If you're looking for influencers, then the things that might be useful would be things like page ranks. You want to look at, I've forgotten the word for that, the centrality. You want to look at centrality algorithms. So things like PageRank and so, where those give you an idea of who are the, what are influential nodes in a network. It could be people based on who they talk to and who the people they talk to. It could be things like you're looking at network and IT management and you're trying to figure out what are the influential components or points that, would cause issue if there was failure. So that you want to be looking at a centrality algorithm. So these are clustering algorithms. So hopefully that helps answer that question. Okay, so we have done this good stuff. So how many of our nodes, just have a quick look, how many of our nodes do not have a similarity relationship? So let's do match the person where not exists. I remember this, actually I think it's when not. I may have got this wrong. Let's have a look. Where not similar to and return count p. How many do we get back? 101. And how many did we say we had in there? Okay. Oh, okay. So the easy one probably was just said how many of these we do have. So, okay, so we only have, so we had the cutoff there. So we've ignored a load of nodes straight away. We've made we've decided some rules about what we class as dense or not. So we've already gotten rid of a load of nodes. And what did we put in? I need to remind myself what top TK 50 means, but anyway, we've gotten rid of a load of those, so happy days. So a question that Ranchak has asked again. Can we use this thing to enhance churn models? It may be useful. Again, this is not my area of expertise, but I could see how you could use community detection in conjunction with finding an influential point within that community to try and look at things like churn detection. So the idea being that you identify your communities and then you identify, using centrality to find out who are the influential nodes within that community. And then, if they're unhappy with their service, you can predict what's going to happen around that. So that may be useful, but you're going to have to, I would recommend doing a bit more research on it, but definitely I could see how it could potentially help, but you'd have to do some research around that. Okay, so we've got 795 nodes that have a similarity relationship. So let's continue. Done that bit. So we expect a measure of distance. And where high numbers correspond to items that are more distantly related. So our similarity score is the opposite, where the high numbers correspond to items that are more closely related. Okay, so what we are doing here is, so we are flipping the number. So what's happening in this step here is we're going to match every single one of those nodes that have got a similarity relationship, and then we are flipping the value. So basically, the higher that number is, remember we've got similarity. It's been written onto these relationships between two nodes, and it's going to be between 0 and 1. So 0 would be 0, but we've not written any of those in because that would be a waste of time. And then 1 is going to be like similar, identical based on the parameters that we've put in. So what we're doing here is we're flipping that. So everything that had value of being very similar is going to be dissimilar and vice versa. So let's do this. Okay. And right, let's look at our distribution scores. So I do not, you know what we should have done? We should have tried out Adam's new charts app. So I'll do that next time. I haven't had a chance to use it yet, but next time we have tables, I will get it ready so we can have a play with that as well. Okay, so let's have a look at what's going on here. So what we're doing here, so we are finding all of the person's limit to. Now, bearing in mind, with no similarities, that we'll end up with two relationships because you're going to have a similar to relationship going from P1 to P2, and there's going to be a similar relationship going from P2 to P1. So this little trick here, this is super handy if you're trying to stop duplicate results coming back, is to just say where the internal ID of one is greater than the internal ID of other, or vice versa. So you get the idea. And then what we're going to do here is we are we're getting the distance, star by 10 divided by 10. And okay, so what we're doing is we're getting the symmetric distance between, counting the pairs and the rounded distance. Right, okay, cool. So these ones are the most, where it says 0. So bearing in mind that we did that flip, didn't we? So these were the ones that were similar before. So that now come down as 1 and 2. Okay, cool. Plot the results. Let's look at the diagram. Nathan has done it for us very kindly. So we have, what are we looking at here? So we have a few pairs of coherents that are very close together. Okay, so we've got some interesting groupings going on. Now we're going to do some transformation of our data. So okay, so this is where this idea of how many, we talked about, we'd define what density means for our cluster. So here we're saying 3. So how many neighbors do you need to go out before you say, yep, that's the startings of a cluster? And that's being set to 3. So let's pop that in. Okay. And now we are going to calculate the core distance. So this idea of 3 neighbors. So let's have a look what's going on here. So we are saying match P1 person. So yep, same idea again, pulling these similar people. So with the people, now bearing in mind that you could have the P1, there could be a number of people coming off that. So we're going to find the minimum distance, so the minimum value that we've got on that relationship. Order by distance. Okay, so we're doing the ones with the smallest value. So remember, we flipped those. The small value means they're most similar. Then with P1, we are collecting the distance as neighbors. Okay, so that's creating an array of our neighbors. And then we're saying the core distance. So remember, that's like the number of people. This is like a measure of density. We have got, so P1, the core distance. So that property is going to be coalescing neighbors. So that's going to be our array there, -1. So that's going to be the second value in there. And if that's null, so if this doesn't have that many neighbors in there, it's going to be set to 2. Okay, that makes sense so far. Right, let's make that happen. So yeah, so what's happening here? Because this would give us a value. So we've got to remember that this is always going to be, if this value in the array exists, it's always going to be a value between 0 and 1. So if we get a value of 2, I think we're probably going to have a query down where it's just going to go, if it's got 2, just ignore it. It's not interesting data. Right, so let's do that. So I'm just going to quickly see how many nodes came back with a value of 2. I'm quite curious now. So let's do match p person. Oh, actually, we can just do this, can't we? Straight away. Port dist is 2. Remember, we had about 795 nodes, didn't we? With similarity relationships. So how many have been ruled out? Let's have a look. Oh, 27. Okay. 27. So we had 27 characters who weren't very well connected. So they are probably not going to be continuing in our journey. Okay, so let's do the next bit here is we are going to calculate the mutual reachability. So that mutual reachability, that's all about saying who are my closest neighbors? You know, how many, how close am I to you? How close are you to me? So that's our mutual reachability, rather than this idea of, for example, with k-means, where we're just looking over every single point in our data set and then going, well, okay, with every single data point, how far apart are we? This is all about this sort of local looking at your neighbours. Like, oh, look quite close, that's nice. So that's what's going on here. So let's have a look at what's going on here. And we are, I'm going to have to remind myself what that APOC function does. Let's have a look at the description here. Okay, no, so I think this is, distance. I think this is, we're collecting the distances. So let's just have a, I'm just going to quickly remind myself what this does. Okay. Oh, this finds us the maximum value in our array. Okay, so we are taking our M1 and M2 values. Now, bearing in mind that we may have more than one M2 here because it's going to be a number of those. And we've got the distance, and we're taking whatever is the largest value of those, and we're setting that to mutual reachability. Okay, right. Off that goes and runs. And we are done. So we're setting that on the relationship. So, oh, this is exciting. Right, let's take this and look through what's happening in this query. So we have got, aha, I believe she's a baddie. That is the length of my knowledge of Game of Thrones goes, so please forgive me. Okay, so we are going to match Cersei. And we're going to find all of the people that she is similar to. She's a queen or something? Oh my goodness. I think my Game of Thrones is significantly worse than my Star Wars. So we are going to go off and find all of the people that Cersei Lannister is similar to. We are then going to return the distinct names of all the people that she is similar to. And then what we are going to do is we're going to take the chord distance and chord distance, the distance which was the max that we set, and the mutual reachability. So quick look at what's going on here. So we said, so the chord distance was, if you recall, we went to the third, went to the third element in the array, and we took the distance in there. So that's the chord distance that is coming up in there. We then took the mutual reachability distance. So that was the case of looking between the ones, and then we have the distance and the mutual distance. So got those values. So let's have a look at what's going on here. The mutual reachability is determined by the second person score, not sources, which that makes sense. Okay, so if we talk about the mutual reachability, because that's slightly different, because if you're thinking about what's happening with the groupings, it's not necessarily dependent on one person, because you're thinking about if you think about a route that you're taking and you're thinking about the different sort of like the min spanning tree, and you're looking at the different points you need to get to, it's quite possible that you'll have other things that are clustered together and you fit in that cluster, but it doesn't necessarily mean that you're the center of that group. So it could well be that if we were looking for the influencer, so I think we were talking about finding the influencer network, it could well be that in this cluster, Cersei Lannister is not the influencing node in that network, although she is part of that network. So maybe, well, I'm kind of tempted to have a little play and see what happens next. Let's see if it's covered by Nathan's blog post. But okay, so it could well be that she is not the influential person in this network, which is why we're having this interesting stuff going on. So let's have a look at the next one then, which is look what happens. There you go, Kevin. You're coming in there with your knowledge of Game of Thrones. Graph of Thrones is one of my colleagues named it. But yes, as Kevin was saying here, is that the closest one is Jaime Lannister, and they were a couple. So there you go. Right, let's have a look at this one. Oh, didn't mean to do that. So we've got Baxter with Cersei, similar to P2, and we're looking for distinct nodes for P2. We want to get the mutual reachability and difference. So I think Kevin's already on this. Yeah, so that's the average distance. So they're all quite close, I think, there. So even though we had the different variations, they're all quite close in that network there, aren't they, in that group? So closely knitted in that cluster. And I think we've got an example here of a minor character. Okay, so I'm not going to run this one, but we can have a quick look. But you can see you can see all the values here are a fair bit smaller than the values here for our minor character. So his few neighbours are either very close or very distant. So you can kind of get the idea is that maybe this is a cluster of maybe 2-3 individuals, and then that's it. Then the next ones are like miles away. So I think here we're going to see quite large average distance, aren't we? Yeah, 0.35 versus 0.01, so that's quite big. So his network's a bit more sparsed out, whereas here within Cersei's, they're very close together. So lots of interactions, very similar. I want to apply this to the ingredients later, I think. I think that's what we're going to have a go at HDBSCAN on. Okay, so transform data, building the minimum spanning tree. So I know normally we only do an hour, but I'm hopefully you're not in any rush. I'm quite happy to hang around. So I'm going to finish this blog post. I think this is fun, and maybe we can throw in a bit of centrality as well to see what happens, because I'm intrigued now, I have to say. So we're going to build out the minimum spanning tree. So we talked about minimum spanning tree. That is it's a way for us to figure out the best connected things together. So if we've got a bunch of points and we want to figure out what would be the minimum distance to join them all together, and it's almost like what you might use for the traveling salesman problem, but to bear in mind that you'll have backtracking up and down points, and the point being is you don't necessarily have a choice point, but it's the way is what's the minimum basically tree-like thing to join all your points together. So we are going to be creating yet another projection, and let's talk about what's going on in this projection here. So again, we're creating one. We're calling this GO2 similarity. I should delete and drop the graphs. If we get problems, then I'll delete and drop the graphs. But anyway, so we got similarity. So we want person. It's person node again, and we're now using that similar to relationship that's been created. We're interested in the mutual reachability property. And again, we're not worried about direction. So let's load that in. Okay. So what's next? We've got minimum spanning tree. So the thing to bear in mind with minimum spanning tree is you do have to give it a start point. So obviously, depending on what start point you pick, you can end up with different trees. So Sansa Stark, I don't know who she is, but we're going to be going with Sansa. I assume she's a fairly major character. And we are going to pick that. So yeah, so I think the common way that they do the minimum spanning tree stuff for HDBSCAN is to use Prim's algorithm, or there was another algorithm that was spoken about in that video I talked about. So we don't have either of those. So we have an implementation of minimum spanning tree. And for the purposes of this, minimum spanning tree is minimum spanning tree. So that's what we're going to do. So we're doing minimum spanning tree. We're given our start point, which is Sansa Stark. Necra tells me that she is quite a character. Excellent. And we're going to run it on our projection. We've defined what our start node is, which is going to be the internal ID of this node here. And again, we're saying what properties we're using. So we want to use the weight property of mutual reachability. We're writing. So we're going to be so with minimum spanning tree, what you do is you will write a property or something like that. So here we are going to be writing, and this would be writing the relationship. So this creates relationships between your nodes. So it's going to create one with a type of MST, and it's going to put a property, which is going to be the distance. And okay, I'm going to yield some stuff. Right, let's do this. And just for entertainment value, we can show the minimum spanning tree as well. What we can do is if we do this I'm living dangerously now. I don't know how it's going to cope with. How many relationships did we say we had? 65,000. I will bring back a few, not a crazy number. Actually, what I'll do is I'll do this one. If I click a minimum spanning tree, then it'll bring back 25. There we go. Oh, whoa, baby. Because it's done this. Hang on, let me just quickly turn off the setting here, and then we'll run that again. So if I take off return connecting nodes, and let's just rerun this. There we go. So you can see little fragments of our minimum spanning tree. And if I double click on this character, oh no, that did what I did not want it to do. Anyway, you get the idea. So we can start seeing this. And if we brought this back, you'd have like a little tree with dangling nodes and all that good fun. Okay, right, so we've done that. Oh, we're going to use Bloom now. Oh, actually, that's a good point. We can look at the minimum spanning tree in Bloom. So let's do that. I'm going to come back here. I'm going to start Bloom. So I will need to give it some details. I love the randomly generated passwords. They're so amusing. Okay, so let's go to Bloom. Give it some amusing credentials. So what I can do now, I can bring back the minimum spanning tree and we can have a look at that, and that'll be good fun. Ah, okay, look at that. Thank you very much. I will take this readily generated thing. So the only thing is we may not have minimum MST in here. So we may need to, oh no, it's in here. Okay, we are good. So if I do something like person MST, no, I think, oh no, there is. So this is going to give us our fun. Everything's connected like a tree. Oh, look at that. Wow. Ah, actually, I've just realized I think this is what. Yeah, look at that. Exactly. That's where Nathan's going this. So what we can do is we can now look at the hierarchy, because this is a tree. And you think about, we're going to have some child branches, and you think about how minimum spanning trees working, how it may go down a route and then come back up again and all of that. So we're going to have a very interesting visual going on here. So let's do that. Let's activate the hierarchy feature. And look at that. And what's interesting here is we appear to already have some settings on our node. So let's have a look at person nodes. We've got some rules based on here. We've got page rank on here. Okay. So we can probably change these. So for those who were asking before, so page rank is showing who the influential people are across the entire network. So we may actually be able to, so we may already be able to have a look who are the influential people in the clusters already. Although this page rank will be across the whole global or everything, not to individual clusters, but we can get an indicative view of what's going on. Okay, that's exciting. That's a big purple blob. Let's have a look at big. Jon Snow. I do understand that he's very influential. And page. Yeah, he's got quite a high score. Okay, cool. Right, so we have looked at that. So you already got hierarchy and you can see how everything's being linked in. So we are going to okay, we're going to do clusters now, so let's see what's going on. So cluster size of 1, find the 2 clusters that are closest to each other and then merge them into a single cluster and then repeat that 2. Okay, so this is like this crystal growing that we spoke about earlier. And this idea of you're going to find 2 nodes and they're going to find, if they're close to each other, and then you're going to start merging together and you just keep slowly growing them out, the ones that are close to each other. And that's going to keep going to a certain size. So you've got this idea, look, it's that diagram, this dendrogram. And this idea of is trying to figure out, do we have 1 cluster? Do we have 2 clusters? Do we have, and it's this idea of distance where we're basically saying, well, how many, how many neighbors do we need to have before we define you as a cluster? So you can see, you can either go down the route where it's like, sort of no points, like everything's its own unique individual cluster. And as you go up for number of points, number of neighbors, then obviously the number of clusters drop down. So there will be some nuance as to how we figure that out. So we looked at that. So we start the relationship tree that has the lowest weight and then merge a cluster into the relationship. We'll then move to the next lowest weight relationship and continue merging until we have exhausted all the relationships in the tree. Oh, that was exciting. Okay, so let's have a look at the function. We are going to be creating a custom function, epoch. Those of you may have seen we did this with the k-means when Nathan put together the stuff for k-means. So we went off and put it into a function, and he's now given us a function to run the clustering. Kevin's very excited. I know it's exciting, isn't it? Yes, you can do custom functions and procedures in Cypher with epoch. So cool. Okay, so what have we got? So we are saying, so the name of our function is getLastCluster. And what we're going to do here is we are going to match the nodes where the internal ID equals a given internal ID. Then with the nodes, with the node, we are going to match a path where that node, so nodes are anchor up to C. So what we're saying is C. Okay, no, that's just a match. So we're going to then go out a number of steps. So it's basically from 0 to many. And with that path, we are going to order by length the paths. So we may return a number of paths from that anchor point descending. So we're going to order it by the largest length to the shortest length, limit 1. So we're grabbing the longest path out of that. We're then going to return we're going to return the -1, I believe, is the last node in that. Yeah, so we're returning the last node of the group of nodes that we've returned as last cluster, and the name node. Okay, it's an array false. Okay. Right, okay, let's do this. This is exciting. Let's create our custom procedure. Right. All right, we've got the description for it as well. So what we're going to do now, we are going to run our custom procedure or custom function even. So we are going to match all of our nodes that have the minimum spanning tree relationship where m.evaluated is null. Aha, so we're putting a flag on our relationship there to make sure we don't keep reusing it over and over again. And so matching we don't have that. So at the moment, that's going to be everything. But obviously, as we run this, that's going to get less and less. And we are going to order by the minimum tree distance. Remember, we added that as a value when we were minimum spanning tree. So we want to find the smallest one. And we're going to get the first smallest one. Then we're running this function on A, because A we know is connected to the one with the shortest distance to B. And as you remember, that's going to pull the paths, run down the route, etc. Oh, we're running it on B as well. It's cluster 2. Then we are creating our... Well, when did we... Oh, okay, no, so we're saying that the node return back is going to be a cluster, and then we are going to then connect the... Where's C in here? Let's have a quick look. Oh no, so C cluster and cluster 2. Okay, so what we're doing here is we're creating a new node called cluster. So that's the new node we're creating here. I'm giving it a C. And we're attaching cluster 1 and cluster 2. So those are the two things that we ran here. So we ran it on A and B. And they're being connected into the same cluster. And then what we're saying here is we are setting the values to those two, which is the minimum tree distance that we had previously there. We're hooking those in. And then we're now setting properties on that new node that we've created. So we're giving it a size, which is going to be the number of nodes we had in that first path, number of nodes we had in the other path. We're saying that they've been evaluated, that relationship here has been evaluated, so we don't need to include it again. And then we're going to return everything. So we're probably going to run this several times. So let's just, oh no, it's going to run everything in the data set, isn't it? So let's run this. Let's see how long this will take actually to run. Oh, that was fast. So I think that may have just run on 1, but that was the one that had the shortest distance. So I assume this has got something puny. Oh, minimum distance of 0. I mean, you can't get smaller than that, can you? And you've got the distance there, and you can see they're in this cluster called 2. So there's just 2 of them. Now, okay. So, Gunther, you'll all be shocked to hear that I don't know who Gunther, son of Gurn is, or Shrouded Lord. The first 2 characters to be joined in a cluster. We see that it's 0. Right, let's see that. Let's see who they interacted with. Ah, okay. Oh, you know what I did? I need to just put the relationships back in, or I can just do this. Let's turn the relationships back on. We've done what we wanted to do. Okay, so if I rerun this, they'll all have their connections together. So you can see the interactions. The interesting thing here to say is there is no similarity relationship between these two, and that will be presumably because they weren't similar enough. So maybe these are minor characters that didn't really talk to each other. Yeah, I know, Kevin, I forgot I disabled the canary resulting nodes. Well spotted. So you got those ones. So I suspect what happened is that these, dare I double click? Oh no, it did. Okay. Let's get rid of that. Too many nodes. Too many nodes. But they obviously didn't have enough interactions to say that they were close enough to be similar enough. Right. Let us continue. So we are now going to run this. So here's our good friend periodic commit. So what that does is that just keeps, quickly talk it through. We want to iterate. We want to keep running the same thing over and over and over again. And a nice way of doing that is to use periodic commit. And what periodic commit does is you basically give it something to do. So this is, you give it a query, and then you can give it some parameters. So usually you might use this if you've got a limit or something like this. And a limit or something like this. But here, because we're not really worried about passing any parameters, so what we can do here is we can say, well, this is the function we want to run, and it will run it, and APOC will keep running it. And then one thing you need to do as a safety mechanism for periodic commit is you always have to return something, and periodic commit will stop when you return 0. So normally we do a count of star. So remember we did this thing where we're using this m evaluated is true, and in our function we had a where we're looking here actually before we start a function where m evaluated is null. So at some point all of our min span tree relationships will have an evaluated property on there, and then that means that when we match this, it's going to be 0. So when we return count star, we're going to return 0, and then it will stop. All good. Right, let's run this. I'm well excited to see what we get back with this. So while that's running, let's have a look here. We're going to do blue. Ooh. Excellent. I'm not going to spoil it. Let's wait until it's come back. Ah, but we did it once. Yes. So I'm using the funky button that we've got here. So yes, Kevin, that's right. So we ran it the first time without the APOC periodic commit, and that just showed us what happened. And that's only going to run on the first 2 nodes that we selected, because remember we had that limit 1. So if I go back, let's go back to the query. I can just quickly show you what's going on here. So you can remember that we are doing this order by min spanning tree limit 1. So this is only going to bring back the 1 pair of nodes. So yeah, absolutely you're right. So we only ran it once, so we only changed those 2 nodes. And then we use the periodic commit to then do it. So again, it's running it once for 2 pairs, but it's just keep running it over and over and over again until that condition of returning 0 is met. So yes, that's exactly what happened there. Okay, so we've done that. We have, yep, that is all run. Excellent. So we are going back to Bloom. And let's clear the scene. We've got some instructions, haven't we? So we are going to refresh perspective. And that's just going to check if we've got new labels and things. It'll go off and assimilate those. And add a category for cluster. Oh, yeah, I see what we're doing, because we created a new node, remember? A new node label called cluster. So we're going to add that in here. That's pretty straightforward. We just do that. Well, obviously, the dead people was too morbid for the perspective that comes with this sandbox, so it got left out. Okay, so we've got the size. Okay. Oh, I'm really excited now. You know what I'm going to do? I'm going to do this person cluster, aren't I? I'm going ahead of myself. So person and cluster. There we go. Ooh. Oh, that's interesting. So this is expected. Oh, we've reached the limits. That's why we were being told we need to do the settings. More nodes. All right. Let's do that. 27. Living life dangerously. Ooh. Right, I'm going to take off the hierarchy so that they... Oh, no, it didn't do what I thought it was going to do. It's clear to scene and start again. And... Oh, hey, look at that. This is exciting. Oh, sorry you have to go, Necra. We'll see you later. But catch up with the video later. So if you have to go now, it'll be on YouTube pretty much straight away. So you can join in where you left off. And yeah, we will go into more details of the cipher. Absolutely. It's all good fun. So see you later. Right. We're not stopping, by the way, those of you still here. We're still going. Oh, we've got some clusters. Ooh. So that's interesting here because we should have got a few more. So I think maybe what I'm going to do here, I'm going to expand in cluster. There we go. Got a few of the members. So we need to see what's happened there. So if I do, I'm going to clear the scene. And if I do person cluster person, I think it's inadvertently putting in the direction. So hopefully if I do this, this should bring... Ooh. That's exciting. Right, let's have a look. Oh, so set up that, and we've done in cluster. I'm not getting this nice tree. I feel a bit left out. Let's have a look what's going on. Let's clear the scene. Oh, that's more like it. There we go. That's way more satisfying. Oh, look at that beauty. Wow. So let's do this. Oh, look at that. How satisfying is that? My goodness. Wow. So you've got some big clusters here. So look at this one. So remember the number is the number of nodes that we've got in the cluster. So here you've got a cluster of like 157 people. 158, 59. So the only interesting thing here is, oh, these are the hierarchies. Of course. So these are the hierarchies that are going on here. So you can see how it's iterating up as we keep adding a new person in, which makes sense. Okay, right. That's cool. So I think we're going to do something next here, aren't we? So let's clear the scene. And now we've got to condense a cluster tree. So remember we said, so we had that nice diagram, didn't we? Let me come back up here to the nice diagram. This, the dendrogram. So you always see here, we've kind of got that dendrogram, haven't we? Where we've got all of like, this is kind of like everybody. And then you can see like the hierarchies like coming in for the trees. So Kevin said it kind of identifies nodes in a virtual simple way. So I think we're going to do that next, Kevin. So I think now we've got to condense the tree. So we've done the work and now we're going to condense the tree down, which is very exciting. Let's have a look. Oh, look, condense. That's next. Very exciting. So we're saying the minimum cluster size must be 20 or more. So this is where we're probably going to start chopping bits and pieces. So let's do that. Let's set our parameter to that. Excellent. So any person node that's attached to a cluster of 20 or less nodes in their first ancestor is minimum size. So let's, okay, so what we're saying here is map 0 on that, where C1.size is less than, so it's less than 20. and the cluster 2 size is greater than or equal to that. Okay, so what we're trying to do here is we're trying to find, so we're almost setting a threshold here of where we're going to do stuff. So, okay, so we're saying is match all of the clusters where C1 is less, so C1 cluster size is less than 20 and C2 cluster size is 20 or greater. And we are then going to match all of the people who are in cluster 1 or any of the children clusters that go off that way. So we're doing that star where we're going to go pointer chasing down the smaller clusters. And then we are going to create in cluster split distance C2. Okay, so we're saying that actually they should all belong to C2 cluster. So that makes sense. What we're doing here is we're saying find a situation where we find a cluster that has 20 or more members, and then all of the other clusters that have a relationship to that one that's got less than 20, and then what we're going to say is they all belong. So all of the person nodes that are all of those smaller clusters, they're all going to be joined onto that big cluster. And then we're going to delete all of those clusters that don't meet that. Does that make sense? So we're going to do a bit of pruning. So let's do that. Excellent. And we're now going to do cleanup. So we're going to delete all of those smaller clusters in that situation. Perfect. So just removed 207. We should have seen how many clusters we had. Hey, it's all good. I think if we go back to Bloom now, we should get a different story. Oh, no, we've still got our tree. I think we still have a bit more to do, haven't we? So what's happening next? We are then, refresh maybe. Oh, no, I think we've got a bit more work to do here. Yes, let me quickly refresh. It should be all right. Refresh data. No. Although I think we've got fewer items on here. Because it still makes sense, because don't forget we still have the tree. So we've got the hierarchy of those nodes falling in. So what we're doing here, let's have a look. We are okay, so we are matching. Oh, we're matching cluster, which is in the cluster C, and you've got C2 which is in the cluster. So we're getting three clusters where they're inward bound into this one here. So bear in mind that the C1 and C2 are going to be smaller than C. So, okay, so C, and what we're saying here is where C1 is greater than or equal to the minimum cluster size, as is C2. So they're all going to be 20 or more. And the same idea again, where what can happen is because of this palindrome pattern going on here, we effectively bring this path back twice. So we do that little trick again with the internal IDs so that we just make sure we pull it back once. And then with the split distances, we're going to unwind the clusters. Okay, so we're putting those two together as an array. So this is a little cheaty trick if you want to do some kind of loopy type thing. So you put them together in an array, but wrapping them around the bracket, and then we're going to unwind them as cluster. And then for each one, we are inversing the split distance as lambda, and then we are set cluster birth, cluster lambda. Okay, so we're not actually changing here. We're just looking at some stats. Okay, let's see what happens. Oh, we're setting a property. Okay, so a quick look. If we start top of the tree and work away, then we can see that many branches represent one or two nodes breaking away. Yeah, we know that because that is the pattern of a spanning tree. So this is where we're splitting some of the communities now, aren't we? So, okay. This is probably where we're going to find the root. All paths lead to this node. So this is, do you remember we had 795 nodes where we had characters that were similar? Do you remember the first time we ran the node similarity? So what's happening here is this is our root node. So if we have a look at the query, so this is, because this is the only one that's not in the cluster, because all the other clusters feed in. So remember, if we go back to here, you can see where, if I zoom in, you can see how it's iterating, so everything's feeding in. And if we go down to the very bottom, I'm just going to zoom out and then zoom in. You'll see this one's going to be 795. So that's that one here that we just found. So we're looking for the root one. And we're just going to say it's the, it's 0 because it's at the top of the tree there. So we're saying here, as the nodes near the root, our cluster corresponds to bigger distances, whilst leaf nodes tend to correspond to smaller distances. That kind of makes sense. So the inverse split distance, the lambda value starts small at the root and increase towards the leaves. Okay, so we're going to use this. So this is where we're going to do that chop. We're going to start chopping bits of that tree and turn them into clusters. Well, this is exciting. So we're going to label the nodes just as before. So we're matching all of the clusters where something's not in cluster. So basically this is saying, okay, so where it's not the root, or I want that's associated to cluster birth, set cluster death, return C. Oh, this sounds exciting. Okay. And we are going to be using, final task in this section is to merge all of the nodes in the path from cluster birth to cluster death into a single cluster. Oh my goodness. We're using path expander. So what path expander does is it allows you to go down a path expand and pull things out, and you can set patterns and things. So it's very cool for that. So let's have a quick look at the first one. So here, what we're doing with the path expander is we've found the node we want to start at. So this is going to be a CB cluster birth. And then what happens here is we're specifying what direction do we want, an inbound or outbound. This is our relationship type. And then this is basically not the node of cluster. I think that slash means not with cluster. If I have to remind myself of the docs. And basically you say like how many depths, how many paths down, etc. So that's the first path. So that's basically saying, so path expander is really good if you want to do more specific breadth or depth first dive down into your graph. It's really, really good for stuff like you want to specify a pattern of relationships going in this. If you want to do some drilling down a supply chain, so that's a very, very cool function. And this is how Nathan is using it with regards to drilling down certain node groups that we're saying these should be clusters. So that's the first part, pulling all those nodes together. So we're yielding the path, and then we're pulling out all of the nodes. That's what we're doing, pulling all of our nodes. We've got a nice little array of nodes now. And then here, we're going to refactor the node. So I'm just going to quickly remind myself what this function does in detail. Okay, so right, whilst that's loading, I'm just going to copy this. Ready for us to execute it. Okay, so merge nodes. Okay, that's fine. So it's just going to merge all the nodes into one list. Fair enough. So all nodes are merged into that node, onto that node too. Okay, so that's cool. So this is allowing us. This is like the. This is like the anti-dense node function, which is cool. This is handy. We've got to think of some fun use cases for this. So effectively, what's happening here is we've got our merge list, and we're going to be merging them together in a group. So let's do that. Hey. Okay. And we're going to do some cleanup. So getting rid of the in cluster. So that is going to match anything that has this in cluster relationship, which it comes off as C. Now, so remember we had cluster birth and cluster death. So there's some labels. So let's go. Ooh. Right. Time to have another look. Oh, hello. All right, let's clear the scene. Let's run this again. Oh my goodness! All right, hang on, let's turn the hierarchy off. I think I'm going to rerun this because sometimes. Start again with the hierarchy off. Let's get us some clusters. There we go. Now we're starting to get those nice clear clusters, and now we can start to investigate some of the groups going on. Ah. So we've now got 15 clusters. So we had like loads of clusters. Yeah, we can do that. That's all right. Yeah, we can do cluster, but it's the same. So one thing I'll say is that's pretty much the same thing. So this cluster and in cluster, something in cluster, that is exactly the same thing. So there's a thing in Bloom. I'll give you an example. So you get this thing called filling the gap. So there's 3 different ways we can run that same Bloom query. So we can do cluster, I could do cluster, and this is called filling the gap. So this will go off and any relationship between the two join it together. Now we know it's in cluster because we've been doing this data. So that's one way of doing that query. Another way we could do that query is just do in cluster, because we know that's the relationship type that joins cluster to cluster. So that also works and gives us the same result. And the third one we can do is cluster, in cluster, cluster. Oops, and I spell cluster correctly. And this will also be exactly the same thing. So here you go, cluster, in cluster, cluster. All 3 of those options will do exactly the same thing. So, oh, I've got to press enter. Got used to that. Okay, that was not, because we're not bringing back the person nodes. Actually, no, you're right, cluster. I think that's, I missed the subtlety there. But yeah, so you got the clusters, so you can see where they're joined. I'm sorry, Kevin, you were right. And I completely, because I forgot you have other relationships coming off the in cluster as well. My bad. Okay, so yeah, we can see we've got how they're joined together, and I assume there's going to be a great chop soon. So we've got the remaining clusters, and we want to select the high quality clusters for our output. We'll use the lambda, which we calculated as 1 over split distance to guide our choices. Okay, so what we're doing here, we are going to be matching clusters. Again, we're going to be matching all of those nodes, basically all 15 that we've got left now. And then what we're going to be doing is we're going to be summing that lambda we talked about here minus the birth lambda. So that's the one that we set earlier. And we are going to coalesce the size if it exists. And if it doesn't exist, then we're just going to set 1. and this is stability. And we're going to set them as selected. Okay, cool. Right, let's see what happens. Set us some properties. Which should be up here somewhere. That should be pretty quick. And adding a new label. So everything where not in cluster. So this is going to be everything but the root cluster. I should set. Okay. And we're now going to start splitting things furthest from the root. So root's like the top node where everything comes in. So yeah, no, the sandbox has been put for its paces, isn't it, Kevin? And okay, so we are going to, so we're looking for the nodes that are further, the clusters that are furthest away from the nodes. And we're going to start doing some chopping. Oh, how exciting. So let's have a quick look at what's going on in this query. Okay, so we are matching, again, we're matching the path. We've got a cluster, that's in a cluster, it's in a cluster. So effectively, this is our anchor point. So it's going to be the top of the cluster. That's in cluster. So this could theoretically, so this could be the root node here, or it could be iterations thereof. So if you think about what's going on here, is this could be many paths. So if you think we've got, let's say we've got a chain of 10 clusters. So we've got a root cluster, and then its child and its child and its child. So you could see where that could be the root cluster, then it could be the child, and then the child's child, and so forth. And then we're saying it's its neighboring child cluster, and then we are running down to the bottom, the lowest branch, lowest child there. We're putting that path. So this won't include, so if you've got 2, so it won't go to the second last child or the last child here. And then we are taking the length of our path. We are taking the max path length, so we know what the length of is. We know what the maximum length is. So bear in mind, we're going to have lots of different branches and things. So we're getting what is the longest path down that one, which is undoubtedly going to be the root, and then its children down to longest little branch somewhere. We are ordering this from largest to smallest. And then we are going to collect C. So we're going to collect all of this middle node here, the child of that starting node as clusters. We are then going to unwind. We're creating a range. So we're going to create a range of 1 to the number of clusters we had there as a rank. Then we are going to get the last, the number, the second last. This is where we do some array stuff in here, aren't we? That's rank, and then we are going to set the evaluation order to rank. So that's what we're saying is, if you think about the long path, so let's say we've got 10 as an example, we're then going to say, well, actually, we've got 10 items and things, so our range is going to be 1 to 10 as rank. We have unwound that, and we want the -1, so that's going to be 9, and then we're setting 9 to our evaluation order. Okay, cool. So we're going to do that to most of them, not the small child. That's been done. We are then going to compare the parent stability with the sum of the child stabilities. So let's have a look at what's going on in this query here. Make it a bit bigger. Okay, so our good friend periodic iterate, which means we're going to be running this a number of times. So let's have a look. So we are matching cluster where evaluation order is not null. So there we're setting the thing to check whether or not that has been evaluated, that process. So remember, periodic iterate wants us to return 0. So that tells it that this is complete. So this is what we're going to use. So at some point, we're going to match a cluster where well, we won't be able to return anything, so it will return 0. Okay, then we are going to match the valuation order, child. Quickly check what's going on here. Okay, so yeah, the stability was based on the 1 over distance and the lambda. Okay, fine. So, okay, so we've got stabilities. We are summing stabilities. Fine. We've got an epoch do when, so that means we have a condition which, when it is fulfilled, we are going to make changes to the graph. So in this example here, we're setting the parent stability to the child stability, which we're saying is the sum of the children that come off of that branch, off of that path. Then we are setting a label. So we're going to be setting a selected label. And then we are removing the, if we set a selected label onto the children, those are all coming off. Fine. So we're using labels to figure out what nodes we've triaged, which we have not. Then we keep going until we've set an evaluation flag and everything. Okay. Let's see this in action. Cool, so that's applied to the 6 paths. Again, remember, this won't have affected the last child node or the one next to it. So we had 15. So I think how many branches we had. This is, now we want to go back into the hierarchy mode. So these ones here will have been left. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we said 6. So this one's not going to be touched. So I think these, no, that, sorry, my bad. So it's going to be long paths. So this, and this. Yeah, okay, so it's the longer paths. So that's what's going on in there. And clusters that retain the selected label are the final output. Okay, cool. So let's see this. We're going to get a bunch of names. So let's have a look in Bloom as well. So we can start seeing some of those clusters. So that's really cool, actually. Nice. So we've been left with 6 clusters. Cool. Okay. So that's what we've run back. We've got those. So our algorithm placed 463 characters in clusters. So remember, we had 795 characters, remember, when we did the similarity. So 463 of those have been placed into clusters. 332 are not in the clusters or not being selected. So they probably are not some level of interaction, not a huge amount of interaction. So let's have a look at, got here. So we are looking at match P person where not in cluster selected and P interacts. Oh, this is interesting. Which makes sense. So Right, so I can see what's going on here, and I've noticed that Nathan's on Twitch as well. So, hello, Nathan. I hope I'm doing justice to your blog post. So the interesting thing here about this is, again, with my very limited knowledge of Game of Thrones, I know that Jon Snow's an interesting one because he's got quite a high page rank, and I believe Arya is interesting, and Daenerys as well. So this is the really interesting thing. So if we think about what HDBSCAN's doing, so it's all about trying to pull the tightly connected groups together and pull them into clusters. But what it's probably not going to do so well is what happens if you've got certain characters or certain nodes that span different clusters. So this is where it gets quite interesting, because if you think about what's happening here, we're trying to find clusters, and we had this terrible idea of noise. So some of the points in the data that we have when we're trying to cluster in this example here, they don't necessarily fit into a cluster, and they would be ignored. And that kind of makes sense, because if you think about the kind of interactions that you're going to have certain interactions where you've got super dense nodes, like super connected, things are working together. And then you're going to have some of these nodes that don't necessarily fit into any one cluster. And that would make sense. I think from my very limited knowledge of Game of Thrones, as I understand it, Jon Snow has lots of interactions with different characters. So he will have lots of interactions with different communities. So he's not necessarily going to fit in there. And as Nathan talks about here, that absolutely, that makes sense. And what becomes interesting here is when you start fitting this in with other things, such as trying to find, I've forgotten the name, but when you want to start finding your linkers, your bridges between your communities, then you can start to see that these could potentially, if they've got mass interactions with different groups, and this is where we start using different algorithms, these could be your bridges that tell you how you can connect those two communities together, or more than one community. But absolutely, it makes sense that they don't connect. Cool. So that is HDBSCAN. This has been really exciting. I wasn't even aware of HDBSCAN until I sort of went off and gave a good read of this blog post, and I'm really excited because I can see a lot of really exciting graphy things that you can apply this to, and it's really powerful if you think about trying to pull out potential hierarchies as well. So I think we can have a lot of fun with that, and it's definitely something I'm going to investigate. Thank you very much for joining me today. I know it's been a longer session than we normally do, but I think we all learned a lot. We had a great bit of fun there. So thank you very much for joining me, and I will see you all again next week. I will hover about once I stop this. If you've got any more questions, pop them in the chat. Otherwise, I hope you have a fabulous day, and I'll see you all next week.